Hi, this is video number 8 in this little video series about the matrix groups SO2 and O2. And in this video, we're finally going to talk about the terminology of orthogonal. So that's this letter O here, special orthogonal and orthogonal group. So I've been using this terminology, calling SO2 the second special orthogonal group. So of course this second, that's where the 2 comes from. And the special, that's where the S comes from. And the orthogonal, that's where the O comes from. And of course I also told you that we are assuming the entries are in the real numbers. So there's that as well. I think maybe at one point I wrote SO2 semicolon R or something like that. So we've seen this, and similarly with the orthogonal group O2, this just takes out the special. So this is just second orthogonal group. And this is self-evident that that means 2. That's where the 2 goes, and that's where the O comes from there. So we're focusing on this word here, orthogonal. And then, of course, we'll talk about special as well, and that comes in with this determinant condition later. But so first, orthogonal, the reason why these are called orthogonal groups is because, so I'll just tell you this and then we'll talk about the details. So because the rows, well, let's say it like this. Why is that word orthogonal there? So if A, B, C, D is an element of O2. Now remember, SO2 is a subgroup of O2. So this would include the case where this matrix here is an element of SO2. But if you have a matrix that's an element of O2, then the rows, so there's 2 rows, right? There's this row. I guess we don't really need a comma there. So we could say the set of rows. So I could open up brace here. So that's the set of rows. Let me name this matrix. Let me go ahead. Name this. I don't know what you want to call it. Maybe A. So if A, and then this is the definition of A. That's what A is. So the rows of A form what's called an orthonormal set. And that's orthonormal set, and it's of course of row vectors because they are rows. So of row vectors, and the columns, and we could write out what the set of columns are. This would be A and C is the first column, B and D is the second column. The columns of A form an orthonormal set of column vectors. So that's the meaning, and I guess if I underline orthonormal set before, I'll underline it there as well. Now, I have to tell you what an orthonormal set of vectors is if you haven't had a lot of linear algebra. But this is the basic meaning. That's where this terminology for orthogonal comes from. And you would really be justified in calling them orthonormal matrices. I mean, you could call this the second orthonormal group. We don't do that. I'm just saying it would be justified because orthogonal is a little bit less specific than what orthonormal is. Orthonormal means something more, as we will see. But I've run out of room here, so let me clear this off and we'll start talking about then what does that word orthogonal mean. So I've told you why orthogonal shows up in the definition of SO2 and O2 because the row vectors and the column vectors in a matrix in one of those groups satisfy this orthonormal condition, but now I have to tell you what the meaning of the orthonormal condition is. So this is meaning of orthogonal. And then also, we're going to have to talk more specifically. So, and more specifically, orthonormal. And this is, all right, so let me see how I want to group this. This is linear algebra stuff. See if I can spell. So, two vectors are orthogonal to each other if they are perpendicular. So this is a synonym. So orthogonal is a synonym for perpendicular. And of course that means angle of pi over 2 between them. Now this is a geometric description. I mean, I'm trying to figure out how best to make use or how to make my board stuff look neater here. So let me group that. So let me write it like this. So this is a geometric description. But up here I wrote linear algebra stuff. So we're making a geometric description of sort of an algebraic thing. And so the definition is really going to be in algebraic terms. And so we'll talk about algebraic there. But this is the thing to remember. And this is what it came from. This is, you know, sort of the algebraic viewpoint came from trying to capture what the meaning of this geometric viewpoint is. So I can have vectors, and I think of these as arrows. And you know, they could be row vectors or column vectors. And they could be in a higher dimensional space as well. And there's all kinds of abstract generalizations of this idea, but I'm just drawing here some sets of vectors, and they could be any length you like, and that doesn't look quite like a right angle, but that's supposed to be. Let me redraw this one. Let me draw something like this. They could be the same length, or they could be very different lengths. But the thing that's common about all of these pictures here is that the angles, there's all these right angles here, pi over 2, pi over 2, pi over 2. So this is the thing that we're wanting to capture. Now, in this particular context where we're talking about SO2 and O2, the vectors that are involved here are very concrete. They're just ordered pairs of numbers, and you can think of them either as columns or as rows. And of course, we'll have to think about both sides of that in terms of the matrices, because it turns out that, like I wrote before, that the rows of an orthogonal matrix are an orthonormal set, and the columns are also an orthonormal set. But so this word orthogonal in the geometric context, this is what it means, that you just have vectors that are at right angles. Now you could have, so here I wrote 2, and the reason I wrote 2 is because of this 2 here, because we're thinking about set of just 2 vectors at a time, either row vectors or column vectors. But you really could have more. I mean, you can have as many as you want. So you could have more orthogonal vectors. And the prototypical example is this sort of 3-dimensional coordinate system where you have an x direction here and a y direction here and a z direction here. So here, of course, the x direction is supposed to be coming out of the board toward you. So it's like here, this is the floor down here. This is the floor. And then this is the left wall. And then this is the back wall here. And so you have a little vector coming out towards you like this. And you have one going that way, and you have one going that way. And they're all perpendicular to each other. I mean, these are all right angles. That's a right angle there. That's on the left wall over here. And then there's a right angle here on the floor. So you think of that as sort of like a floor tile, that little square. And then you have a right angle here. They're all at right angles. So you could have more, but for us now, it will suffice to just talk about 2. Let me erase the, well, all this sort of commentary because I need this space. And then, so this is geometric description here, geometric description. So what the algebraic description would be, so I'll say 2 vectors, and I will name them here because I'll need it to write an equation. So I'll write u and v. So these are vectors. And I could have done the same thing up here. I could have written u and, let's see, that's messy. I could have done the same thing in this geometric context, written u and v. And then, of course, when I drew my pictures, I could have named these, right? So that's a right angle. This could be u, this could be v. I didn't do that before. But here, 2 vectors, u and v, are orthogonal. If their dot product, and so this would be written u dot v is 0. Now, of course, ultimately you would replace this dot product, this particular dot product, with a more general notion of an inner product. So this would be more general. This would be what's called an inner product, of which the dot product is an example. The dot product is one kind of inner product. But in general, there are all kinds of different sorts of inner products for different types of vector spaces. And in this case, the one that we're interested in is just the dot product. Now, it may be that if you, for some reason, you haven't had linear algebra, then maybe you haven't encountered the dot product, or, you know, if you have, you would see it in a physics course. That's another place you would see it, where you're talking about forces, like, you know, the component of force. Like if you're trying to figure out what the work is, for instance, it's the force dotted with the distance vector you're moving, provided that you're moving, that it's a constant motion, that you're not changing direction and stuff. So That's the product that we want here. And the way this is defined, so I'll just write e.g., this is right down here at the bottom. So if we're talking row vectors, for instance, if u, this vector u, is a row vector that has two components, u1 and u2, and v is a row vector that has v1 and v2 as its entries, then u, see if I can just fit this in down here, u dot v means u1 v1 plus u2 v2. So the way you take the dot product, if you've forgotten or if you are not familiar with it, is you have a vector, you have components of that vector, and you're just pairing the components one with the corresponding components are the ones you're pairing. The u1 with the v1, the u2 with the v2. You pair those together and then you add them up. So I'm going to have to clear this off, and then we'll be a little bit more specific and more precise about the dot product and orthogonality in this context. So this is more details about orthogonality in this particular context, which is, row or column vectors with two entries. And we're using the dot product. So you remember I wrote this, so I said something to the effect that if A, and then I wrote this, A, B, C, D is an element of, let me fix this, of O2, then let's just look at the rows. So I'm going to abbreviate here. So I'm going to have the rows A and B and C and D. Form an orthonormal set. Now I've told you what orthogonal means. I haven't told you this normal part. I've just told you orthogonal. I haven't told you the normal part here. So there's really two parts to this. One is that they're orthogonal. And then the other part is that they're normalized. So we saw what the orthogonal meant, both geometrically and algebraically. It would mean, well, here since we have the A and B and the C and D, then this would mean the fact that these two vectors are orthogonal to each other would mean that, well, it's just the first component here times the first component here plus the first component here times the first component here. And so this, what all this is saying is that AC plus BD equals 0. That's all it means. Now, what I'm not going to get into, this is really linear algebra thing, what I'm not going to get into is showing that this algebraic condition actually makes the geometric condition I showed you work, that it actually makes the vectors be geometrically perpendicular to each other. That you'll have to take on faith, or else you'll have to look it up somewhere else, that this algebraic definition really accomplishes the geometric meaning that we want, but it does. So there's two parts to this. There's this orthogonal part, which would mean this, that these two vectors are orthogonal to each other. And then there's this normalized part, and this, what normalized means is that you have each vector is of length 1, exactly 1. Now what the length will be, this would be using the Pythagorean theorem. So this would say a squared plus b squared. Well, the length is really the square root of that. This is equal to 1. And then this would say c squared plus d squared, square root of that, equals 1. Now, the reason why, so if I have a, say I have a coordinate system here, and I'm kind of running out of room, but say here's my vector here, say this is my row vector AB. So that means that, so if I drop a perpendicular line here, there's a right angle there, and that's saying that this distance here is A, and it's saying that this distance here is B. Now, you know from the Pythagorean theorem that this distance here is none other than what I wrote there, square root of A squared plus B squared. So for this to be orthonormal, this word normal here, let me give myself room to underline it. This word normal, it means length 1 in this context. Length 1, that's what it means. Now you can express this in terms of the dot product, and I'm running out of room here again. So you can express in terms of the dot product. This is getting a little bit messy, but if I just name this vector u, this vector I've been calling AB, if I name it u, then, well, u dot u, what is it? Well, it's that thing dotted with itself, so it's the first component of u times the first component of u, so that's A times A, and then plus the second component times the second component, so that's B times B. And of course, what is that? Well, that's A squared plus B squared. And that's going to be 1 in this case. That's what normal would mean in this particular case. So the length is really, of course, the length here is really the square root of the dot product of this thing with itself. And that you've known that since like 7th grade, right? Because that is just the Pythagorean theorem. So we have these two things that they have to be orthogonal and they have to be normalized. Now there are concise ways to write this, and you could be more abstract. You could be more abstract and say that a set of vectors. So I'm going to have a whole set of vectors now. So this will be v1. Well, I don't know. I'm not going to write it. Yeah, I guess I will write it like that. See, this could confuse you because you could think that these are components of a certain vector, but they're not. These are different vectors. So, you know, for instance, this v1 here, this would be v1 would have its own components, v11 and v12, for instance, if we're still talking about 2 by 2, well, if we're still talking about vectors with 2 entries. But here, obviously, if we have n vectors, we might have more entries than that. So each of these is supposed to be a vector now, and they're each supposed to have some number of entries. You know, it might be n, for instance. That would be kind of a typical case, because you can have n independent vectors in an n-dimensional context where you have n entries to each one. But you could be more abstract and say that a set of these vectors is orthonormal if I take any two of these. So if I take the one labeled I, so we have 1 in here, you know, I is in here somewhere between 1 and n. And then I take the dot product of that with the one labeled j. So j is somewhere else in here, somewhere between 1 and n. And I doesn't have to be less than j, but it doesn't really matter. In any case, you could say that if I take the dot product of these two, well, it's one of two things. If I is not equal to j, then it's just going to be 0. And if I is equal to j, then it's going to be 1. So what's the significance of this? Well, this first condition here is saying that different ones are orthogonal. So if I take different vectors, that they'll be at right angles to each other. And then this condition is saying that any individual vector, well, I'm be a little bit precise there. So well, let me say it like this. Let me say each has length 1. That's what this is saying here. Now you can be even more clever. Well, you can make this an even more compact sort of notation by using this thing that they call the Kronecker delta symbol. So there's this. This is kind of a highbrow way of saying it. You know, if you want to appear clever and sophisticated, and so on. So you would say here, vi dot vj equals, there's this delta thing, which is I, j. And this is written in a variety of ways. I mean, sometimes they'll write they'll write a lower index and an upper index or something. But this thing just means, this thing is what's called the Kronecker delta. And it just means something that does this. It means something that's it's just a symbol that has a value of 0 if I is equal to j, and it has a value of 1 if it has a value of 0 if I is not equal to j, and it has a value of 1 if I is equal to j. So you can be as sophisticated about this as you want. And you know, there's other things that you can do. So this is kind of other details. Of course, you can think about this dot product as a matrix multiplication. I mean, you could say I have u equals u1 and u2, and then I have v equals v1 and v2. Now, in this case, these are components. So here, up here, the v1 meant a whole vector. Here, it just means components. Let me be clear about that. You can write u dot v. Of course, I showed you what this was. It's u1 v1 plus u2 v2. You could write this as, if you wanted to, you could take the u1 u2 like this. And then you could matrix multiply this by converting this row vector into a column vector. And then it's a matrix thing. So if you wanted to, you could write this, and I'm running out of room here, you could write this as U times V transpose. The T means transpose. And then, well, I guess I won't write the dot there because then it looks like a dot product. This would just be matrix multiplication way of thinking about it. For some reason, I can't seem to write accurately here. And then another thing, like I said before, the inner product that you're using is not always the dot product. It is in this particular case. But in general, you would replace this dot product with what you would call an inner product, and it would, the symbol for that would be like this. And there are other inner products that are not, that's inner product. There's other inner products that are not the dot product, and I'm not going to tell you about what those are now. So the last thing I want to do in this video is just take a few examples of rotation matrices and reflection matrices and show that they satisfy this orthonormal condition. And that's actually quite easy to do. And so, I mean, the reason I put all that abstract stuff in the middle, I guess, is because if I showed you the examples first, maybe you wouldn't have watched all the abstract stuff. So, examples of this orthonormal condition for, and I'll just say O2. So, well, I'll say matrices in O2. And like I said, SO2 is a subgroup of that, so this is included. So this is for matrices in O2. Well, we can take what's on the board. Let's look at that rotation matrix there. There's a little bit of a glare up there. I don't know if you can see what that is, but let's take this matrix. I'll call it A in this context, and I'll recopy it here. So this says square root of 3 over 2 minus 1/2, 1/2, and square root of 3 over 2. Well, what are the rows? There are two of them. This first row is square root of 3 over 2 and 1 minus 1/2. And the second row there is 1/2 and square root of 3 over 2. So if I wanted to, I could call this my U and this my V. And if I wanted to, I could call this U1 and this U2. And I could call this V1 and I could call this V2, just in terms of what we were talking about before. So if I do that, I'm going to use that here, and I'm going to erase it. I'm going to use it down here, but I'm going to erase it here because I need the room. So if I take this off, and if I say, if I call this vector U and this vector V here like this, then I'll tell you what, I'll put a U up here and a V up here, so that way it won't be in the way. Well, we could look at, so we need to check some things. So first let's look at U dot V. What does that mean? Well, it means U1 V1 plus U2 V2, and then we can write out what these are in terms of what I said those are there. So this is U1 is this, so this is square root of 3 over 2. Let me be a little neater here. So this is square root of 3 over 2. That's the U1. The V1 is 1/2 plus, and then we have minus 1/2, and we have square root of 3 over 2, and I can just fit that in to erase my little divider line here. And so you can see what's going to happen. This comes out to be square root of 3 over 4. And this comes out to be minus square root of 3 over 4. So that's equals and then equals 0. So that was, remember I wrote the two conditions there, that the different vectors, you take the dot product and you'll get 0. And so I've done that. I've taken the u and the v. So the next thing to check is what happens if I take u dot u. So thing here. So we got u dot u. What would that be? Well, that would be this here. So this is going to be u1 times u1. So that's going to be u1 squared. u1 squared plus u2 squared. So that's going to be square root of 3 over 2 squared plus, here we have minus 1/2 squared. What does that come out to be? Well, this is going to give us 3 over 4 plus 1 over 4, and that's going to give us 1. And then so we had one more to check, and that's v dot v. And so this would be v dot v, that's of course v1 squared plus v2 squared. And we see what those are here. This is 1/2 squared plus square root of 3 over 2 squared. And that's 1/4 plus 3/4, and that's 1. So what this all boils down to, and I'm going to have to erase this and use the space again, is that u dot v was 0, u dot u was 1, and v dot v was 1. And these together say that u, v are an orthonormal set, because that's what orthonormal means. That if I take different ones and take the dot product, they give me 0. If I take the same ones, then they give me 1. Now you could do the same thing with the columns if you wanted to. And I'm not going to do that in detail. You know, you could just start it. So if you looked at the columns, what would those be? Well, there's two of them. There's square root of 3 over 2, 1/2. And then there's minus 1/2, square root of 3 over 2. And I can play the same game. Now, these have the same numbers in them as what the rows did, so I think it will be pretty plausible to you that these will also be orthonormal. Well, this was a particular rotation matrix that we used. Now, I also have an expression there for a general rotation matrix. And you see, this is no harder, and it's going to involve a trig identity, and you probably know already which trig identity. So this is for the general rotation matrix. And so that's this one here, cosine theta minus sine theta, sine theta, cosine theta. And we can play the same game. We can look at the rows, for instance. Let's look at the columns first this time, because we looked at the rows, and I'm not going to do both, but let's look at columns here. What are the columns? Well, they're cosine theta and sine theta here. And then the second column is minus sine theta and cosine theta. And so I could call that one my u, and I could call that one my v if I want to. And then I could check, well, what's u dot v to begin with? It's u1 v1 plus u2 v2, which is, this is U1, that's U2, that's V1, that's V2. So U1, V1, this is cosine theta times minus sine theta. So this is minus cosine theta sine theta. And then U2 times V2, that's this times this. So this is plus sine theta times cosine theta. And you can see immediately that's 0. That's the negative of what that is. And then I could take U dot U. And so this is U1 squared plus U2 squared. So that's cosine squared theta plus sine squared theta, and that's equal to 1. That's the most famous trig identity, right? And then so V dot V, this is V1 squared plus V2 squared equals, and then we have, well, this is a minus sine, so this is minus sine theta squared plus cosine squared theta, and that's going to equal 1 too, because this minus is going to square away, and so I'm going to get sine squared plus cosine squared equals 1. So once again, these are an orthonormal set. If you take different ones and take the dot product, you get 0. If you take the dot product of one of them with itself, you get 1. So these work. Now, it's probably not too difficult for you to see, if we took this example of a reflection matrix, that this would be in the rows or the columns of that would be an orthonormal set. And then similarly with this general reflection matrix, you're going to be getting essentially the same identity, the trig identity. It's just you'll have 2 theta instead of theta. There's one minus sign in here, and what that minus sign will do is it will make the dot product be 0 if you have different rows or columns, and it will make it be 1 if you have the same row or column, because it will square, and the square will make the minus 1 go away. I'm not going to write that out because this video is already too long. But that's what orthogonal means, and it's something where you can kind of understand why that would be related to these distance-preserving, shape-preserving type of transformations, which is what these are doing to the plane, because they're keeping things that are at a certain angle, they're keeping the angles the same, and they're keeping the lengths the same too, because the vectors, the dot product of a vector with itself, one of those orthonormal vectors is going to be 1. So anyway, that's all I'll say about this, so we can check this off. And in the next video, we'll talk about the transpose condition, which is very closely related to this orthogonality condition.